Hey y'all, this lesson is for calculating confidence intervals for a one population mean when the population standard deviation is known. That's a mouthful. So confidence intervals are used when we want to estimate the population mean given a certain level of confidence. And so this lesson is for estimating that population when the population mean when the population standard deviation is known. In the next video, we'll do when the standard deviation is not known. So this will be pretty fun. In the last lesson, we looked at a confidence level of 95%. And that was an easy 2 standard deviations above or below the mean. And so we didn't have to do a lot of figuring necessarily. Sometimes we want to obtain confidence intervals of different confidence levels. So first, before we get into that, let's just look at a quick picture of the bell curve that represents 95% of the data. So this relates back to the empirical rule where we have normally distributed data that follows a, that's really bad, bell curve, roughly, bell curve with the mean in the middle, the center, it's a measure of center, and then 95% of the data falls within 2 standard deviations of the mean. So this data in here represents 95% of the data. Which means that for the next question, how much of the bell curve is not shaded? Well, if the area under the bell curve is equal to 1, and we know this is 0.95 in decimal form, then we can figure out the piece that is not shaded, since we know that the whole thing is 1. So 1 minus the part that is shaded is 0.05, but it's split in 2. So each little piece here is 0.025 or 2.5%. So that's really going to tie into what we're about to look at today. We're going to be kind of focusing in on those little tails. If the shaded region represents alpha, then the 2 unshaded pieces on either side represent, so what did we do? We said that the this was 1 minus alpha, and then this is, I think I worded that wrong, but I should say the unshaded region represents alpha. Then the 2 pieces are alpha over 2 because we divided them in half. So what I'm saying here is a little typo, but if this whole thing represents alpha, then when we split it in half, it's alpha over, each piece is alpha over 2. So for this and other confidence levels, we use alpha, where alpha equals 1 minus the level of confidence in decimal form. And also remember that the z-score indicates the number of standard deviations a given value is from the mean. And one more thing we're going to pull in from another video was z sub alpha represents the z-score that has an area alpha to its right. Remember, the z sub alpha represented the right tail. Whoops, you can't see that. There you go. I think that was when we talked about the standard normal curve. I think that video we talked about how the area under the curve using the z tables The areas in the table were the areas to the left, but then when you did Z sub alpha, it represented the right tail. So it's kind of hard to keep it straight, but I think if you can draw a picture whenever you're given information of the curve, that it really helps. Z sub alpha over 2 denotes the z-score with an area of alpha over 2 to the right. So Z sub alpha over 2 is the z-score associated with that area. So up here, the z-score associated with this area is 2. Okay. Let's go back here. Draw a bell curve to show alpha, alpha over 2, and mu. So if you want to pause it and try to draw it on your own, go ahead and do that, and then come back. So we have a bell curve, mu in the middle, and then we'll just say this is 1 minus alpha, and then this is alpha over 2, and then these two pieces added together, I'll move it up in a second, equal alpha. So hopefully that little picture helps you. Okay, now we get to do some stuff. To calculate a confidence interval based on a certain level of confidence, when the population standard deviation is known, these conditions must be met. And this is very important. So you might put a little star or something by these little conditions, because these little things that take up a very small portion of our notes these things are very important, okay? So before we can do a confidence interval based on standard deviation, these conditions must be met. The sample has to be random. So in the problem, it has to say a random sample, or the sample was selected randomly. Also, the population must be normally distributed. If we don't know anything about the population, then the sample must be large. And remember, for a sample to be large, it has to be greater than or equal to 30. So it's one or the other. Both would be great, but it's one or the other. Either the population is normally distributed. If it says nothing about the population being normally distributed, then you have to look and make sure that the sample selected was random and large. And then the last thing for this one is that the population standard deviation is known. If it's not known, we'll do the next lesson. So in order to find the z-score associated with the confidence level, you can use your table or you can use your calculator. In your calculator, remember that we use inverse norm. So use a table to find the z-score that corresponds to alpha over 2. That's an alpha. Looks kind of funny. Looks a little bit like a fish, but that's okay. And then the formula for a confidence interval for estimating the population mean is x bar plus or minus z sub alpha over 2 times population standard deviation over square root n. That is a lot of variables, okay? But if you look at them separately, if you can break it apart in little pieces, then you'll realize it's really not that bad. So we have the confidence interval for estimating the population mean. So we don't know the population mean, but we want to get an estimate of maybe where it could be. You will have to have the sample mean. This symbol plus or minus means that you're going to add and you're going to subtract, and that's going to give you your lower bound and your upper bound. Lower bound will be with the subtraction, upper bound will be with the addition. Z sub alpha over 2 comes from the z-score associated with your confidence level. So in order to find a z-score, you have to have a confidence level. And then this is your population standard deviation. And then this is your sample size. So you might want to write that out. X bar is the sample mean. Z sub alpha over 2 is the z-score for the confidence level. Sigma is the population standard deviation, and N is the sample size. We're out of room. So if you can find each little piece, then computing the confidence interval is not hard. We also call this the z-interval procedure because it has a z-score. And here's some little caveats for using the z-interval procedure. For small samples, which are less than 15, the z-interval procedure should only be used if the population is what? What did we say up here? What were the conditions? If the population is normal. So if the sample size is small and it doesn't say anything about the population being normally distributed, then don't do a confidence interval. If they say this population is normally distributed and the sample size is 10, then you can proceed cautiously. Medium-sized samples are between 16 and 29, I believe. Yeah. The z-interval procedure is okay to use if there are no outliers and the variable under consideration is still normally distributed. Okay, so this is basically saying, if I were to sum this up, if you have a small or a medium sample, it's okay to do a confidence interval as long as the population is normal. And then large samples are 30 or more. You can use the z-interval procedure without restriction. The population does not have to be normal. It does state that if outliers are present, that you should compare the confidence intervals with the outlier in it and with the outlier taken out of it. And then if there's a substantial difference, then you might need to use something else. I don't think we're going to run into that in this class, but if you go on into statistics, higher level statistics, you might run into that. Which part of the confidence interval is considered the margin of error? Okay, so if we go up here, we know that this is the sample mean, and then this is kind of our buffer. It's going to be give or take this amount. So we call that amount, that give or take, we call that our margin of error. So that gives us our little wiggle room, if you will. So the part of the confidence interval that is a margin of error is the plus or minus z sub alpha over 2 times this stuff. The standard deviation for the sample mean is what that stuff is. And then I don't think you're going to see any of this, but I just went ahead and put that in there. The sample size required for a certain confidence interval can be found by using that little formula, but you probably won't see that. If you do, that's your z sub alpha over 2, that's your population standard deviation, and then that's your margin of error. And then you square it. So there's that. I always want to say, any questions? Because I'm used to teaching face-to-face where I can say, are there questions? But you can't answer me. So I have a little table here. This table is actually usually in textbooks given to you, but I wanted us to go through and find it. Now remember that the z sub alpha over 2 is referring to the right tail. So if I were to draw my little sketch, this is z sub alpha over 2, and this is alpha over 2, which indicates that, I'll show you the first example. For a 90% confidence level, that means that your 90% is in here, which indicates that the two tails are going to add up to 0.10. But there's two of them. Oops, you can't even see that. So divide that by 2, and we get 0.05. So this little tail is 0.05, and this little tail is 0.05. And I'm going to fill out my little table. 0.10, 0.05. So if we're going to find a z-score associated with that piece, there's kind of two ways you can do it, okay? I have my table here. We could find the -1, knowing that 0.05 is to the left, because remember, these areas represent area to the left. We're looking for a right tail, but these areas are areas to the left. So we could find this z-score associated with this area, knowing that it's actually going to be positive. It's symmetric. Or we could find the area, the z-score of the area for this whole piece. And I'll show you. I'll show you that you're going to get the same thing, kind of the same thing. If I did 0.05, this is an area of 0.05, and so we're going to be using the inverse of the table, or if you're using a calculator, inverse norm to find the z-score. So if the area is 0.05, that is, let's see, 0.05 looks to be about here-ish, kind of in between here. That is associated with the z-score of -1.64. But I know that I'm actually looking for this one. So it's going to be its symmetric value, which is positive 1.64. I think it's actually 1.645 if we're going to go one more decimal. Or if you are nervous about knowing, is it positive, is it negative, you can use the fact that we want this z-score, and the area to its left is 0.95. So we go to our table, and my table is not big enough. So instead, if you have the z-table little thing from your textbook, you can use that. Or you can use your calculator. You'll go to second vars, down to inverse norm. My area is 0.95, my mean is 0, my standard deviation is 1, enter, 1.645. And that gives me the positive value that I was actually looking for. So that one's a little more accurate. You don't have to do any guesswork there. So now I want you to do the same process for 95% and 99%. I will say it helps to draw a picture. That's going to really help you grasp what you're looking for. So if you can, you should draw a picture and then complete this table and come back. Okay, if you drew your own pictures, you should get, let's zoom in here so y'all can see it. 0.05 is alpha, so 0.025 is alpha over 2. And then when you find the area to the left of that z-score, no, sorry, yeah. The z-score associated with that is, if we round, 1.960. And then 99% is 0.01 divided by 2. Area to the left is 2.575. So these confidence levels are associated with these z-scores. Now, you don't have to memorize those z-scores. Those are going to be z-scores that you see over and over and over again, so you might memorize them by default, by just seeing them. But you don't have to memorize them. If you know how to find them using your calculator or your tables, then you don't have to worry about storing information that you don't need to store. So I would store, instead of memorizing z-scores, I would store how to find the z-score so that no matter what the confidence level is, you can find it. And remember, drawing a picture helps. Okay, so we have an example here. We're calculating the confidence interval by hand of this information with a confidence level of 95%. So our formula, I'm going to skip down here, is x bar plus or minus z sub alpha over 2 times the standard deviation of the sample mean. So in order to find the confidence level, what we need to know is the sample mean, the z-score associated with the confidence level, the population standard deviation, and the sample size. So what we're given is the sample mean, the sample size, population standard deviation, and confidence level. So we don't have a z-score, but we do have a confidence level. So we can use our confidence level to find the z-score. Okay, obviously we just did all the work. So the z-score for a confidence level of 95% is 1.96. And then the formula I already wrote down. So now for a confidence interval, we will just plug in our information. We know that x bar is 20. We know that our z-score is 1.96. We know that our standard deviation is 3, and our sample size is 36. So I'm going to simplify a little bit. 1.96. 3 over 6 is a half. And then simplify even further. I think it's 0.98. So you can write it like that, and that's nice because from that you can easily see your sample mean and your margin of error. But when it's asking for a confidence interval, an interval has a beginning point and an end point. And what it means is there's all these values in between those points where we're 95% sure the population mean lies in. So there's this range of values, and we're saying that we're 95% confident that the population mean is within that range of values. And that range of values goes from 19.02 to 20.98. So how did I get that? I did 20 minus, whoops, wrong line, 20 minus 0.98 and 20 plus 0.98. And so this is your confidence interval. That's the range of values that we're sure, 95% sure, the mean is within. And remember that this range of values is centered upon the sample mean. And then we factored in this margin of error, this wiggle room. So the margin of error is the plus or minus 0.98. Now let's say, for example, I didn't ask for this here, but let's say, for example, you're just given the confidence interval. And from that, they want you to find the mean. Well, we know that the mean is in the center because we based our confidence interval off the measure of center. So if you're just given the interval, then you can find the center by averaging the two endpoints. There's two values, so we know the center is 20. And then if we know the center is 20, then we can figure out how far one endpoint is from 20 to figure out the margin of error. So as long as you're given the confidence interval, you can work your way backwards to find the mean, sample mean, and the margin of error. So we are claiming that this is the interpretation of our confidence interval. We are 95% confident that the population mean, or the mean of all subjects in this study, were between 19.02 and 20.98. I wasn't given units, so I don't know what the study was, but whatever it was, we're 95% confident that the population mean of all subjects is between those two values. Pretty snazzy. Okay, so obviously you probably have guessed, based on my previous lessons, that we can do this in the calculator. Yay! We love the calculator. It's very important to know how to do it by hand, because when you learn to do things by hand, you understand why you're getting the values that you're getting. So like on this example, since we did it by hand, we now know that this interval was based on the sample mean and the margin of error. But we can find that interval quickly using a calculator. So you'll go to Stat, Tests, Z interval, and then you're going to input the stats instead of data. You might be given data, but in this case, you're going to be given stats, and hit calculate or hit enter. So for this first example, we're going to do a calculator because there's a whole bunch of them. If you want to try them by hand and then check with your calculator, I am totally fine with that. That's a great way to practice. I'll do the first one, excuse me, with you, and then I'm going to let you pause it and try the rest using your calculator. So you go to Stat, scroll over to Tests, and then down towards the bottom, at least on mine, it says Z interval. Enter. I want to input stats, not data, because I'm given the literal statistics. My population mean is 3, not mean, I'm sorry. My population standard deviation is 3. My sample mean is 20. My sample size is 36. My confidence level is 0.90. Calculate. And it should come up on your home screen with the interval and then some basic information. So this interval is, whoops, 19.19 to 20.82. So we would say, was it 90? Yeah. Hopefully there's enough room. We are 90% confident that the population mean is between 19.19 and 20.82. That's all. That's all you got to do. So go ahead and pause it. Try the other ones. If you want to, do them by hand. Check them with your calculator, and that way you're getting practice with both. If you don't want to, you can use your calculator. And come back and check your work with mine. All right, so my handwriting got a little sloppy at the end because my hand got tired, but here are your intervals and your interpretations. So we're 95% confident that mu is between 19.02 and 20.98 when the sample size is 36. We're 99% confident that mu is between 18.71 and 21.29 when the sample size is 36. Then we bump the sample size up to 72, and that changes our levels a little bit. So we're going to kind of make some observations down at the bottom. Go ahead and check your intervals and your interpretations. If you need to pause it and do that, you can. And then at the bottom, we have a question, 2 questions. What do you notice as the confidence level increases, but everything else stays the same? So look at the top 3 examples. The confidence level increases, but all other statistics are the same. What happens to our intervals? What do you notice? So we started at 19.19, then it was 19.02, then it was 18.71. So we started here 19.19, and then we went to, if we're thinking about a number line, 19.02, 18.71. So it's kind of like spreading out. If you can picture your number line, I'll show you the number line if you can't picture it. So we have 19, 20, 21, 18. So at first we are more in here, and then it's even closer, not closer, but more spread out, and then even more spread out. So as our confidence level gets bigger, we're casting a wider net on our confidence interval. So if we're going to be more confident, we're going to say, oh, we're 99% sure, then they're going to cast a wider net to kind of capture the possibility that the population mean will be in there. So as the confidence level increases, the confidence interval gets wider. I abbreviated a lot. As the confidence level goes up, the confidence interval gets wider. It's kind of like a bigger safety net. And then what do you notice as the sample size increases? So now go through and look at the same confidence levels, but with different sample sizes. So the first box and then down the 4th box, sample size 36, confidence level 90, sample size 72, confidence level 90. So we have 19.19, 19.42. It shrinks down. If you go back up and picture that number line, 19.19 is about here, 19.42 is about here. So when our sample size gets larger, we have a better idea of what our population mean looks like. This is so neat. As sample size gets larger, our confidence interval shrinks. because we know more about, we can make better inferences. We know more about our population based on a bigger sample. So when we get bigger samples, we get closer to, we get a better idea of what our population might look like. Whereas, you have a small sample, it's probably not a great representation of the population. So as sample size gets larger, our confidence interval shrinks because we're narrowing in on what the population mean might be. So when we know more about our sample, we get closer to our population mean and we're shrinking down that interval. And then the opposite for the confidence level, when we are 99% confident, we cast a wider net to make sure that we've got the population means somewhere in there. And then I have just a couple things to note about the formula. So let's write out the formula first. X bar plus or minus z sub alpha over 2 times the standard deviation for the sample mean. And I want you to fill out this table. Go ahead and try it. You are given certain pieces of information, and you are going to state what is missing for you to be able to compute the confidence interval. So go ahead and try it, and then come back. So hopefully you took some time to figure this out on your own. If you are given a list of data, the population standard deviation and the confidence level, then you are only missing the sample mean. So you might have put sample size, but if you're given a list of data, then the number of observations in the data is how many samples there are. So you can kind of like assume that based on your list, which means that you're really only missing your sample mean. Then if you're given a sample mean and you're given the standard deviation, then you have this piece and this piece, then you're missing a confidence level and sample size. Then if you're given the margin of error, then you're missing the sample mean. Then if you're given the confidence level and the sample mean, you're missing standard deviation and sample size. So that is all I have for this lesson. I really hope you enjoyed it. If you have any questions, please let me know and I would be happy to help. Bye, y'all.